right, so I'll be talking about some interesting applied use cases for AI and maybe, stuff that goes a bit beyond what you might think about when you think of generative AI and chatbots. And so, yeah, a bit about me. Some of you might know me from my work on Spacey. Spacey is an open source library for what we call industrial strength natural language processing. So it was really designed from day one to be used in real products and in production and build natural language understanding pipelines. So if you have a lot of text and you want to find out more about it. And it's an open source project, and we've always put a lot of work into the kind of boring stuff as well, like backwards compatibility, not breaking people's code, and so on. And that had a really nice side effect more recently, which is that, well, in this case, ChatGPT, but also I think you can try it out with Gemini and a lot of other models. They're actually pretty good at writing Spacey code and writing Spacey code that actually works because the API has been consistent. So that's a really nice meta use case. And we also developed Prodigy. Prodigy is a modern annotation tool really designed for machine learning developers to help you create data for models and also create data automatically using, for example, generative AI models. And I'll also show you, some examples of this. And it's fully scriptable in Python. And yeah, probably should have used Gemini here in that little illustration. But it will be featured later on. But yeah, you can use it with any of the models you've seen and write fully custom workflows. And so, as you can see, we really thought a lot about practical applied use cases and stuff companies are actually doing in production and how they're using these technologies. And I wanted to start this talk a bit differently from how I normally do my talks and jump straight into a use case and a real-world example and a case study, which also you can find the links here. I'll also have the slides online as well. And this is a really cool use case from our most recent case study. And what we always like to do is we like to not only really go into detail on what the project is, because I've always hated these case studies where it's just like, oh, we improved blah by 10%. That's a case study. And I'm like, no, I actually want to show what the team built. And we also always like to profile the developer as well. So in this case, for this case study, I actually talked to Jordan, who founded this company. And he has a pretty inspiring story, actually. So I think maybe if some of you are looking to get into the field, you can take a lot of inspiration from this one. And his path to programming was quite interesting because he actually started working as a sound engineer and producer and composer working in music. And at some point, he started getting royalty checks. So, as you know, if you're a musician and someone streams your song on Spotify, for example, or buys a record or an MP3, you get some cut of the money. Maybe not too much, but you get royalties. And so he started getting royalty checks, and really significant ones, like in the tens of thousands, for a country musician of the same name, so not for him. So he tried to contact whoever was in charge of that in the US, couldn't get through, and eventually he just messaged a guy on Instagram and was like, hey, I got these checks here, I think that's your money. And the musician was like, oh shit, like we've been looking, my team has been looking for this money everywhere and we didn't know where it went. So Jordan realized, wow, this is really a problem. Looking into this more, hundreds of millions are lost for artists by incorrect metadata and songs not being mapped to the correct artist, or like in this case, being mapped to him and not to the musician whose song was actually streamed. So he taught himself programming and NLP. Someone, I think, recommended to him he should look into Spacey. That was a good fit for his use case. And so he started founding his company and built tools that tackle this music metadata problem and other issues in the music industry and make sure that artists get paid. And actually his company, with his solution, he already managed to recover hundreds of millions of dollars in royalties and lost revenue for artists. So, it was a very small project. It was just started with a guy who was like, oh, I need to fix this problem. I need to teach myself programming. So he's built AI tools for the music industry and law firms that specialize in royalty negotiations. And really what motivated this was that apparently Spotify, this is also all new stuff I've learned from doing these case studies. Spotify receives 40,000 new tracks a day, and 15% of them contain incorrect metadata. And estimates suggest that like over 2 billion in royalties were lost in the US between 2016 and 18. And some pretty entertaining examples of this, of stuff that can happen, because I was surprised there's no standardized solution for it. So stuff gets copy-pasted around in spreadsheets, and you have things like this, where songs like 711 or albums like 444 are automatically converted to decimals or to datetime objects, and you end up with this. And so of course, of course it's all broken, and the songs that actually get played can't be mapped to the real artist. And now you can say, well, Beyonce probably will survive this, but of course this disproportionately affects independent artists who have no way of actually fighting against this, or even probably don't even know about this. So what Jordan's company built was he focused on components for standardizing music metadata. Again, there wasn't really any standardized system for it, and also the legal negotiation. So companies also used music without actually having a license for it for a given market, and then upload it to, say, TikTok for the US when they've only licensed it for the EU. So this, also labels need to fight for their artists here, and the system also contains components to detect case citations and even predict the outcomes of a negotiation based on what's mentioned in the legal paperwork. And what's really cool about this is that the company and Jordan managed to really develop all of this 100% internally in-house, all the models, all the data to train the models, and also all the applications. And the result is highly accurate models that are really small, and they can also are really fast, because they need to process like billions of song titles and all of these music catalogs from all these platforms. And the models are also private, so they run entirely in-house. And I'll also show you another case study later of like a similarly impressive example. So I think this is all really cool, and I think these use cases have really managed to tackle some of the problems we might be seeing in practice with some of the new technologies. See, here we have Gemini, and with large language models, because as we've already seen in the talk before, we have a lot of new capabilities that we've unlocked. We have really good contextual results that we can get from a lot of these models. And again, as we've also seen just before, really easy to use and configure. You can copy paste the API code and get started. You can use it in your browser, and that also means that this enables really fast prototyping. If you have an idea, you can very quickly get an app up and running, and have something to show. So that's all really cool. But of course, there are also some challenges, which is that, well, a lot of the models are really just black boxes. Some of them are proprietary, and even the open models, you just have this like massive bundle of weights. You can't really look inside. It can make it very hard to debug if something goes wrong, and you have very little insight and transparency. And again, if you're using an API, well, you don't really know what the models are trained on, and what's under the hood and how it all works. And similarly, even though we're seeing a lot of progress and models getting faster, they're still pretty slow. Like even if you're looking at 1 token a second, or even if you're looking at 100 or 1,000 tokens a second, that's slow, especially if you're processing really large volumes of text. And also, if you're using an API, well, you're kind of at the mercy of the API provider. Hopefully, if you use Google's APIs, they probably won't just randomly go down, but if they do, there's very little you can do about it. And then, of course, you also have the question of data privacy. If you use APIs, well, you have to send your data to someone else's servers, and for a lot of use cases, that's not an option. So then you actually need to run models yourself, and then you kind of run into the efficiency problem again. You need a lot of DevOps. It's generally a headache, even if you're using smaller models. It's a lot of work. So the question is, well, how can we fix that, or what options are there for us as developers to kind of get the best of both worlds? And I think if we're trying to understand modern development workflows, one thing that always helps is looking back a bit into the past and looking at how we've solved things before and how we've solved things for different technologies. So, and one thing that's very interesting here is looking at another groundbreaking technology, which is the web. So, in the beginning, websites were mostly static. You might, if you were around on the internet, then you might remember that time. But of course, we wanted a bit more flexibility and dynamic and interactive features. So, with Web 2.0, we added these features either on the server with PHP or in the browser with JavaScript. But of course, it also made the whole thing much more complex and also quite slow. For a while, the internet was actually pretty slow, and it was much harder to set up a website. So we saw a rise in CMS and blogging platforms like WordPress, which you might have used, that took over all of this complexity, often also offered hosting, and in return, you give up some control and some customizability. And some of that is still relevant today, but probably if you've actually built a modern website more recently, you might have used a static site generator that basically takes a lot of that complexity and moves that into the development and build process. So you basically run it locally, it builds you the static website. If you've done web development before, you might be familiar with some of these techniques like tree shaking to really optimize the website, make it faster, and that basically gave developers the control back, and really made it feasible to develop websites in-house, even though they're quite complex. And it's often, I think, what people mean when they say like, oh, web development got so complex and so complicated, but overall it really made the web a better place. And we're seeing something quite similar with AI now. So in the beginning, when deep learning first kind of found its way into companies, you pretty much always had to build your own models using a framework, and that was significant work and significant time investment, and you really had to train all these models from scratch. But with bigger models and better generalization, we're able to use pre-trained models, and there are a lot of new platforms springing up, also, of course, including Google here, which is missing from this graphic as well, sorry. That basically take over a lot of this complexity, provide us with models we can consume via an API, often don't even need to fine-tune at all, and in return, again, we're giving up control, we're giving up customizability, we're often giving up some data privacy, but we get the convenience. But what we're also now seeing is very similar to what we've been seeing on the web, is that with modern developer tooling, it's actually, we can also move a lot of this complexity back into the build and development process, and kind of take back control and make it viable again to develop AI in-house. Also with the help of a lot of the new developments that are available. So we can take all of these large models that otherwise would be quite difficult to host or would be quite inconvenient to consume via an API, and can use them to help us create systems and create smaller, faster, and private, and also generally much better components. So that's the idea, and this process of distillation, it might sound a bit complex, but it's actually, the idea is pretty straightforward. So we start out with a large model, either something you host yourself or maybe Gemini, and first what we want to do is, we have a task, let's say, something information extraction, which is incredibly common in industry use cases, and also what we've seen with the music metadata. You have a lot of data and you want to get information out of it. So the first thing we want to do is we want to have an evaluation, and we want to see how does our model do out of the box. Because if you don't have that, if you don't have a baseline, we kind of don't know if anything we're doing actually makes sense and improves anything. So we start with that, and then we can, as you've probably tried before, we can prompt the model using all the weights we have available, and then pipe that forward into a system where a human can look at it and correct it, because we don't just want to replicate what the model can do, we also want to make it better. So here's an example, that's like our annotation tool Prodigy, so you can stream that in, look at it, if there are any corrections, you can make them, otherwise you can add examples to your training set, and then using transfer learning, we can train a small component that really only does the one specific thing that we're after. For example, make a prediction about our music catalog, extract and map artist names to a database, and so on. And just because there's a lot of talk about in-context learning, so working with prompts, it doesn't mean that transfer learning is outdated or has been replaced. It's simply a different technique, and it's still probably the best technique to use labeled examples and examples where we know the answer in a scalable way. So this is very powerful here, and we can use that in combination with in-context learning to build these components, and we do that until our accuracy beats the baseline or ideally exceeds it. And also, just to clarify here, we're not generating anything new. We're taking text and unstructured data we already have, which usually, in an industry context is often the case. You have a ton of text lying around, and you want to find something in that text, and a model can help you do that very effectively. And then the component that we get out at the end, this is the one we deploy, and that's the one we use in production. And that means we're not, in production, we're not dependent on any API or even any larger model that would be too inefficient to run. So that's the idea. And to show you another example of what's possible using this approach, this is another case study we did with S&P Global, a financial services provider. And what they're doing is they do real-time commodities trading insights and extracting structured data from it. So if crude oil or steel is traded somewhere, they want to provide this live feed to their customers where you can see the trade, the prices, the participants, and so on. So that's also something I learned about by working on this case study. I had absolutely no idea about commodities trading, but this is all information, obviously, that can really impact the economy and move markets. So it has to run in a high security environment, completely privately. Even I went to visit them in the office in London. It's like the analysts are sitting in this glass box, so it's very highly controlled, and that means, okay, models, everything has to run in-house, and no data can even leave their servers. And that's also what ultimately their customers are paying for. They want this live feed as soon as it's available, not before it's sent to 50 different APIs. And so, yeah, that was a very important requirement. And what they actually did was they used a large language model during annotation to help them create the data to train their models. And with some smart decisions, they were able to achieve a 10 times speed up of the data development process with the humans and the model in the loop. And they currently have, I think, over 8 pipelines in production. So this has been a very successful project. And if we're looking at the stats a bit more in detail, we see that not only do we have really high accuracy here and really impressive model sizes. So this is like 6 megabyte. This is tiny, especially in by today's standards. And we have models that run at over 16,000 words per second. So that's really fast. And another really interesting part is if we're looking at the data development time, so that's the time it would have taken a single person to develop and annotate all the data, training and evaluation for one of these models, for one of these pipelines. So that's 15 hours, that's under two work days, or like 1 work day with 2 people. So if you think about like all the stuff you spend time on in your work, you've probably spent more time getting a GPU to run than it would have taken a single person to create data for one of these models. So this is absolutely achievable and absolutely doable with the right tooling and the right model-assisted workflow. And to go a bit further into what's their secret, I think you can really summarize it as one big part of this is actually refactoring, which is something you might be familiar with from your working on code, but I think the same applies to the data process as well, because we have in traditional software development, we have code that goes through a compiler, out comes a program. And in software 2.0, which is working with machine learning, we have data that goes through an algorithm, and out comes a model. And if we want to see how we're doing, we have tests, or we have an evaluation. And now, if you don't like the program, of course you can go and tweak the compiler. And of course there is a ton of work that people are still doing on compilers. But of course, more realistically, you would go and change your code, and the same is true for working with data. The most reliable way, if you are training a model, is still, if the model isn't doing what you want, you probably want to refactor the data, and that also means you want to be iterating on the model and the evaluation until you're happy with the result. How much time do I have left? 20 minutes left. Oh, okay. Okay, good. I'm fine in time then. Thanks. All right. So you now might be looking at this and you're like, do I really need to care so much about this? What if I just want to do something really simple? Do I actually have to spend so much time thinking about it? And I have some small examples that I think maybe illustrate the problem. And one of those is interactive. So this is a simple question. So we have two sentences here. I love cats and I hate cats. And now the question is, are these two sentences similar or not? Who thinks they're similar? Let's do a show of hands. Similar? Okay, who thinks they're not similar? The other half, okay, a bit more, yeah. Normally, we usually, I've done this before a few times, this example, and usually get like 50-50. And of course, as you probably guessed from the question, this was a trick question, and of course the answer is, well, it depends. Out of all the things you can say in the English language, of course these sentences are incredibly similar. They both express sentiment about cats. That's like, really specific. But of course, if you're building a dating app, for example, well, and you're matching people up with their profiles, well, you want to consider these two sentences as very dissimilar. So the lesson here is, well, your application context always matters, and you really can't work on these things in isolation or just pass the data part off to someone who's completely disconnected from what you're working on. Similarly, this also applies to more complex extraction tasks that people are often you want to do more than just predicting whether two things are similar. So this example here, this is from a workshop we did at PyData in New York, where we actually tried out this distillation idea that I showed you earlier, and we did that with a whole group of participants, and we took text from the R Cooking subreddit, and we built a model that classifies extracts ingredients, dishes, and equipment, and we did it live with the audience. And actually, as part of that workshop, we were able to beat the GPT baseline with a model that was 20 times faster and just as accurate with data we created together. And the nice thing about the workshop was that also, of course, there are immediately a lot of discussions. As soon as you start looking at the data, people are like, oh, but what is Cheetos? And you start discussing all of these questions, and instinctively you might think, well, it's actually kind of clear, these categories. If we define dish as like some ready-made product, then Cheetos is clearly a dish. But then it also, if you actually look at the data, it turns out that especially Americans really like using stuff like crisps or chips in as an ingredient in like a meal, or like they also use like Cheerios and cereal and all kinds of, like Cheetos here clearly is an ingredient, and you might have not expected this, but as soon as you look at the data, you're like, shit, okay, we kind of need to rethink our strategy here. And so again, this shows it's really important to engage with the data early on before you spend too much time on designing a label scheme that might or might not fit. And the same is true for other categories. Like if we're thinking about stuff like equipment, rolling pin, pretty straightforward. But then we have something like a small bowl. Is bowl the equipment, or is the small bowl the equipment? And if you say, oh, small bowl, then what about a small and microwave safe bowl, or small and so on? There's like, this can get kind of complex, and you're immediately faced with like, oh, I need to make even more decisions. And part of that decision is also identifying, well, what's actually specific to my application? So we're extracting ingredients, and what's something that's very general purpose, that's actually much more about the language and completely independent from what we're doing here. And the small bowl is an example of that. We do have some features in here. The fact that small is an adjective that's connected to bowl, and that's grammar, and that is how we actually process the sentence, and the reason we understand what this phrase means. And that's something that's actually completely independent from the business problem we're trying to solve. And that is something we can take advantage of. So it can be a big advantage to not try and teach a model all of these things from scratch, and instead focus on the business problems and the actual things we're trying to train here and take advantage of grammar and syntax and other features we have available that are much more general purpose. So a way of looking at this is, as a general tip we'd give to people, one part of the secret is try to factor out business logic, or expressed in a pseudocode formula like this. You apply the general purpose classification first, and then your business logic that's really specific to what you're doing. Because most of the time, the valuable problems you're solving in industry are the things that are really specific. And here, general purpose things are things like words, grammar, syntax, and also stuff that's like really directly in the text, whereas business logic are things like external knowledge and also facts that can change over time. Like if you're classifying devices and phones and you want to find out what the latest model is, you can try and predict that, and with enough data and large enough models, it would probably work, but you could also just look it up and do some maths on a date, which is probably a much more future-proof and more robust approach. And one tip we often give people is, well, if you're unsure, try to think of it from the model's point of view. You're only given that text and no further information. Are you able to make that decision based on the information that's in the text, or do you need any external knowledge or any knowledge about the business problem, and then refactor your task that way? So all of this kind of leads into the question, and I think one of the main problems we're seeing at the moment, which is it's really easy to build like a cool prototype, but a lot of projects don't actually make it to production and kind of get stuck at the prototype phase, which is also something we like to call the prototype plateau. So it's all looking really promising, and then you kind of get stuck there. And and as we've seen, there are some things you can do, and there are some ways you can avoid this. And one tip is definitely, you want your prototype and your production system to input and output the same thing. So, generative AI and generative models that output text are a really great way for humans to talk to machines, or machines to talk to humans. But they're not necessarily the best way for machines to talk to other machines. And a lot of tasks are tasks where a machine talks to another machine. So, if your demo and prototype takes text and output text, but in production it actually needs to take structured data from your database and output something else for a database, then you have a problem. So I think your prototype should ideally focus on taking the same inputs and outputs as your application in the end. And also, while this might not sound like the most exciting topic, it's really important to have a stable evaluation, and maybe even start by really simple evaluations. How far do you get with a regular expression? Like the answer might surprise you. Like if that gets you 98%, do you need Gemini in that application? Maybe not. Or similarly, how well does a generative model do out of the box? All of these questions are really important, because otherwise, if you just do sort of the vibe space thing, that's kind of really how you end up in this plateau, because once you do a proper evaluation, you realize, the vibe space thing didn't quite match the real performance, and it's not good enough, and we can't ship it. So I think having some data where you know the answer and evaluating on that is really important. And that also means that ideally that number that you're tracking should correlate with how useful the system actually is in your application. It might sound really basic, but if we look at research, we can get very focused on leaderboards, and we can get very focused on numbers, but that doesn't mean anything if it's actually not doing the job. And I also linked the blog post we have on that topic that goes a bit deeper into that kind of having the right mindset for actually building something for production. And finally, if you're working with language, we need to consider that language, unfortunately, doesn't fit as neatly into boxes as we would like it to as developers. So there's a lot of ambiguity. We're often just kind of gesturing at things and not really saying things out loud explicitly. And but there's also a lot of structure in language that helps us understand each other that we can take advantage of, like grammar. That's something we shouldn't forget. There's actually a lot of information in that we can really use in the applications we build, and that can be much simpler than trying to teach a model a lot of these things all together. And Finally, all of this, of course, requires refactoring and working on your data iteratively. The first idea, as we've seen with like the Cheetos and Cat's example, maybe might not be what you want to ship and might not be the best idea. Once you start looking at the data, you're almost always going to be surprised by some edge cases and examples, and you might have to completely change your strategy. So at every step of the way, it's important that you know when to stop. You can try out more things, because and a lot of the workflows I've showed you where you could use large generative models to help you do the work. Yes, that makes us as developers a lot more productive. We can have a model that writes code for us, and sure, that means we could do less, but it also means that we can do more and we can try out more things. And I think that's like a really great takeaway from all of the latest developments. So yeah, in summary, yeah, I think it's very important, always take a step back and reason about what you're doing and expect to be surprised by your data once you start engaging with it. I think the right developer tooling is very crucial. You want something that lets you iterate and try things out, and not just scale up, but also scale down. Like in these case studies I showed you, that was spearheaded by a single developer who just went and did the thing. And if we have tooling where you, as an individual, you have a great idea for a model, you can just build it and build a 6 megabyte system that solves the problem. That's great, and that's also the best way to get past yeah, what we've called the prototype plateau. And finally, we've also seen that there's really no need to compromise on software development best practices we've built up over the years, like transparency, modularity, efficiency, and also data privacy. We don't want to be building systems that are worse than what we have currently. And so, you know, yes, there might be, you know, companies or people in the industry telling the story that all you need is a bigger and bigger model, but as developers, the rest of us, we don't have to believe that. So, thanks.